Assalamu alaikum. Welcome to this live stream. We are covering a series on universal common ancestry. And I have with me again Dr. Paul Nelson. Welcome, Paul. It's always a pleasure having you on the channel.
Thanks again for having me.
So we had, I believe, two parts before this. This is part 3, and then we're going to have part 4 on the 18th of November. So over to you, Paul.
Thank you again, Subor. I greatly enjoy these interactions, and it gives me a chance to refine my own thinking, which I really appreciate. So in the earlier presentations, I indicated that the compelling nature of universal common descent for many biologists rests on an intuition about probability and the similarity that they observe, particularly in molecular data. And I think that there are unexplored assumptions or presuppositions that we need to examine. And that is the goal of this presentation and also the next one, which will be on November 18, which will help us, I think, understand why evolutionary biologists hold universal common descent with such a tight grip. And the point of the presentation today and also in a few weeks is to help those biologists and ourselves understand the possible logical minefields, if you will, that they enter by holding those presuppositions. So that's kind of a long-winded introduction, but I hope that this material will be accessible to you. And again, as was the case with my previous presentations, all of the references will be available on the YouTube page. I'll make them available to Subor for posting. So this statement has been received opinion in evolutionary theory for many decades. And I'm sure you've seen formulations like this in your own reading. The origin of life and its subsequent evolution are two fundamentally different scientific questions. So we find in Darwin himself, in the third edition of The Origin of Species, he writes, "It is no valid objection that science as yet throws no light on the far higher problem of the essence or origin of life." And then he draws a parallel to physics. Who can explain what is the essence of the attraction of gravity? And I think that there's a case that can be made for Darwin's position here, and also for that position as it's come down into modern evolutionary theory, that the question of the first origin of life and its subsequent evolution, those two questions can be separated. On the other hand, from this statement, the one there in the green box, the proposition below, which is also widely held in biology, does not follow. Namely, this statement, therefore, the origin of life has little or nothing to do with how we infer evolution or the branching structure of the tree of life. So I'm going to challenge that second statement in the presentation today. I think that a case can be made for the statement above, namely that the origin of life and then its subsequent evolution are different scientific questions. But it does not follow that the origin of life has nothing to do with how we infer the tree of life. That I think is false, and I hope to demonstrate that in the next 40 minutes or so. In fact, I'm going to argue that proposals about abiogenesis, that is the natural origin of life on the one hand, and hypotheses about the relationships of organisms, such as Darwin's monophyletic single tree of life on the other, are as closely connected as any two ideas can be in science. They interfinger logically and evidentially with each other. What that means is what one assumes about the origin of life bears directly on how one infers the evolutionary history of life, its subsequent branching into the diversity we see today. And this is exactly where Sober's paradox comes into play, as you'll see. So, quick outline of where we're going today and then on November 18. Our motivating question, as I struggled to express a few moments ago, more succinctly framed here, is the following. Is there an overlooked problem in the probabilistic structure of phylogenetic inference? So first of all, we're going to ask, where are we on the theoretical landscape? We'll locate our position for the discussion. Then we'll look at a common inferential puzzle in comparative biology.
Paul, can I just, sorry, intervene for a sec? Someone's just knocked on the door. I'm just going to answer it. Just give me a second. Sorry about that. They've gone now.
Okay. The second point will be, we'll look at a common inferential puzzle in comparative biology. And by that, I mean not only classical comparative anatomy, but particularly today, comparative genomics and phylogenetics, and that is observed similarity. Then we'll turn to what I call the consequences of improbable pathways, and by that I mean improbable evolutionary pathways. Then part 4 will be Sober's paradox and what he missed. And lastly, the paradox bites evolution of the ribosome. Now, this is our focus today because we want to keep this a reasonable length. I think very highly, by the way, of Elliot Sober. I consider him a friend. He works at the University of Wisconsin-Madison, which is about 2.5 hours north of me. I am here in Chicago. I have interacted with him in both on the Madison campus when I was a graduate student and here in Chicago when he would come to give colloquia. We've had some correspondence together. And I think of him as really a fine, superb philosopher of biology. I think one of the most thoughtful people publishing today. So please understand that what I have to say about his work should not be taken as an indictment of the quality of his work, which I hold very highly, but really his work is a jumping off point for this presentation and what I'll have to say on the 18th, which is dealing with mainly points 4 and 5. And by the way, I promised in the first 2 sections of this series that I would talk about the ribosome and never got to it. Well, on the 18th, we'll look at the ribosome, really the molecular machine that defines the living state. Viruses, by definition, lack ribosomes. And work that's been done over the past 2 decades on the structure of the ribosome is really, to me, one of the most exciting parts of molecular biology. So we'll spend time focusing on that on the 18th in relation to the puzzle I'm going to describe today. So in this segment, we're going to focus on the probabilistic intuitions which ground our perceptions of shared similarity. And then part 2, as I indicated, we'll look at how Sober formulates the paradox and what he missed that's significant. So where do we stand on the theoretical landscape, or where we stand on the theoretical landscape? I want to define a matrix of opinion that will be useful to us in thinking about that landscape. So it has 4 quadrants. No design and design define 2 positions, and the tree of life existed, Luca, the last universal common ancestor at its root. And the last universal common ancestor, Luca, did not exist. There was no tree of life. So that gives us a matrix here, a 4-quadrant matrix of opinion. Now, the familiar parts of the matrix are evolutionary theory in its textbook form. So we can locate Darwin there. Really, by definition, neo-Darwinians in the 20th century, and then still alive and very active, Richard Dawkins and Jerry Coyne today. So that's textbook evolutionary theory there in the upper left. The other familiar quadrant is creationism. or intelligent design, to give it a name that I think is perhaps appropriate for 2021. And you see there Linnaeus, Cuvier, Louis Agassiz, the last great academic creationist in the United States in the 19th century. My colleague, Jonathan Wells at the Discovery Institute. Gunter Beckley is another colleague of mine. And by the way, Gunter could possibly be moved into the next quadrant as well. It's unclear to me at any moment where Gunter stands on the question of the existence of the tree of life, but I'm going to put him here for the time being. So here we have, in this quadrant, we have design and no tree of life. Now, this quadrant is perhaps less familiar, but really no less interesting. Here we have people like Asa Gray, the theist, Harvard botanist and friend of Darwin. They corresponded extensively. Darwin's co-discoverer of natural selection, Wallace, who especially towards the last decades of his career was outspoken in defense of intelligent design. George Wright and Teilhard de Chardin, both theistic evolutionists. And then Michael Denton and Michael Behe, who are colleagues of mine at the Discovery Institute, both of whom support the historical reality of a single tree of life, but argue for design in various ways. Now, you might say there's nobody up here. That's the least familiar quadrant. In fact, when we look at the history of evolutionary theory, Darwin was very much the exception in the 19th century for arguing for a single tree of life. His predecessor, his French predecessor, Lamarck, did not endorse that geometry. Lamarck had multiple independent origins of life going on, which will give you a forest, not a tree of life. But then coming into the 20th century, we have, for instance, the great Russian zoologist Lev Berg, who argued for a polyphyletic view of evolution. The English physiologist Gerald Caircott, same kind of view. And then more recently, Carl Woese, W4 Doolittle, and Didier Raoult in France, who has run into some problems in the past year or so for advocating hydroxychloroquine as a treatment for COVID infection. But I don't think that should be held against him. He's a bit of a wild man and pushes the box. In any case, this fourth quadrant is becoming increasingly crowded in the light of genomic data. And I've addressed this in previous talks with this group, and other talks that are available on YouTube from me talk about that. The point of putting this landscape up here is to indicate we are going to focus today on just this part. There's an important reason for that. The problem that we'll be discussing is already sufficiently complicated that we don't need to entangle ourselves in the hypothesis of design at this point. So we are going to stay strictly within naturalistic evolution. At the end, we'll come to some questions that open the door to considering design, but to circumscribe the problem so we don't bite off more than we can chew, we're going to stay strictly within theories of naturalistic evolution, asking the question how one decides between these two geometries, a single tree of life or a forest of life. Now, why do this? Why circumscribe the problem? Well, as I said, it's already complicated enough. So here is a logic tree that I have found very helpful because in its absence, if you forget this logic tree, you can create really unnecessary difficulties for yourself analytically. So we have our starting point is the metaphysics of explanation. Are we going to consider the possibility of design? Well, that bifurcates to yes or no, right? And then we have another bifurcation, or another question, excuse me, which is what is then the historical geometry of relatedness that best explains the history of life on Earth? So you could say, as Mike Behe does, there was a single tree of life, or as Richard Dawkins says, there was a single tree of life. So it looks like they're converging at that point in terms of the geometry, or there was a forest of life, or there was a forest of life. So again, this is another way of representing the four quadrants on the previous slide. Now, the problem we face is that endorsing a tree of life as the best geometry for explaining the history of life will appear to draw together two positions which are in fact deeply different, profoundly so, in fact. So what we have here is a case of misleading intellectual convergence, because if you were to ask Mike Behe why he endorses a single tree of life and what explains that geometry, the arguments and evidence that he will give you will diverge radically from those that Richard Dawkins would provide, even though both of them appear to be saying there was this single tree. The actual content of their positions is deeply different at a very, very profound level. And it actually starts up here with their philosophy or their metaphysics of scientific explanation. So, and actually, we can see this, if we consider the forest of life geometry. So here's Jonathan Wells, my colleague at Discovery Institute and a close friend. This is Eric Baptiste, who is a very productive theoretician at the Sorbonne in Paris. Both of them deny that there is a single tree, but they do so for very different reasons. And again, we have a case of misleading intellectual convergence. So again, I want to simplify our problem by eliminating design as a possibility, a causal possibility, just so we can get a manageable framework. And this actually, I could give it a whole talk on this problem. This actually extends right throughout everything you do in biology, or frankly, in science generally. If you raise questions about cosmology or human nature, this would also apply. What answer you give to this question will affect every downstream question, right? It ramifies into every investigation you do. So that, in fact, I would say that this is the deepest divide epistemologically for any scientist or philosopher, for that matter, when they come to the question of origins. So we're simplifying the landscape just to keep the problem tractable. And if, sorry, my little friend here, excuse me, fellow mammal, it is a serious error to regard intelligent design as a causal hypothesis, as simply the logical negation of whatever is asserted by naturalistic evolution. Don't do that. Please, I'm begging you, don't do that. You will create a life of misery for yourself. Much better is to understand that these two metaphysics of explanation have great regions of overlap where they converge empirically in terms of what they predict. There are all kinds of happy benefits that flow from this epistemology, this outlook on how these two theories relate. So that's where we are in the landscape. Now, point two, observe similarity. Let's start with the kind of question that comparative biologists face really as their daily bread, right? It's the kind of problem they face all the time. We have species A and species B, and we clone or we isolate two gene sequences, one from A and one from B, and we align them. And we find that these are cartoon nucleotide sequences. Of course, a real gene would be very much longer than that, protein coding gene, let's say. And we find 95% identity, base pair by base pair, once we align these sequences. Well, that degree of similarity calls for explanation, right? There's a puzzle that we need to give a causal account of. So how do we explain the similarity? Well, we have two options. Either A and B share ancestry, or they have independent origins, which we can represent schematically this way. So on the left, we have independent ancestry. On the right, we have shared ancestry. Now, let's compare the causal scenarios this way. So independent origins on the left, leading to our two sequences, versus common ancestry from some unknown common ancestors, call it sequence X on the right. Now remember, this is what we observe up here. All this down here is inferred. So we're starting here. The observations actually are here. Similarities between A and B, similarities between A and B. And the rest of this down here is inference. So we're talking about a problem of inference, looking for the best causal account to explain what we observe. And we'll have two kinds of probabilities, the origination probabilities and the transition probabilities. Now, next time on the 18th, I'm going to talk about the transition probabilities with respect to the ribosome, the origin of the ribosome and its observed diversity among different groups. This, I won't say much more about this today, but it will turn out to be very significant on the 18th. So this, by the way, is also how Sober carves up the problem in terms of origination and transition probabilities. Now, for most people, including, I would say, the people on this who are watching this right now, the separate ancestry scenario appears much too improbable. So if you go into the literature, this is a citation from the late Gabriel Dover, who was a geneticist in the UK. Interesting guy, called himself sort of a non-Darwinian evolutionist. And actually his last book was, he conceived a series of letters, correspondence between himself and Charles Darwin. Died tragically young, but very active during his career. And in 1987, he said, look, when we see a high degree of similarity above the background level of coincidence, it's got to be homology, meaning a common evolutionary origin. Why? Because to suppose that these sequences could have arisen independently requires us to violate our probabilistic intuitions. Here he says, against the odds. Many recurrent independent origins of similar genes and proteins under freak conditions. So he said, above that threshold background level of coincidence, which for nucleotides will be the alphabet itself, right? A, T, C, G, and DNA gives you a 25% match right off the start just because that's the alphabet. But as you rise up to higher and higher degrees of similarity when you're aligning sequences, Dover argues any other scenario beyond common origin is just implausible. Molecular convergence doesn't happen because it can't. All right. Colin Patterson, also, he was at the British Museum for most of his career, and died in 1994. But in the late 80s, actually the next year, and in a stream of articles actually in which both Dover and Patterson were contributing opinions, he makes the same point. He says convergence between molecular sequences is too improbable to occur, just as similarity is too improbable to be explained except by common ancestry. Again, notice the appeal to probability. Probability dictates, he writes, that these sequences must be homologous, meaning sharing a material template in common, rather than convergent. Now, the bottom line or the take home from this, for both Dover and Patterson, and I would say for the molecular phylogenetics community generally, is that we can count on molecular similarity not to mislead us. Namely, you can have convergence at all other levels, behavior, anatomy, physiology, and so forth. But when you get down to the DNA and you have above a certain threshold, you observe similarity, that is going to be genuine homology. There's just no convergence possible at the molecular level. Now, at first, this makes good probabilistic sense. And I want to credit the strength of that intuition. So this is how we catch plagiarists, right? I mean, if I assign a student or a group of students an essay topic, and one of them or two of them turn in an essay as their own work with this phrase in it, when in the course of human events it becomes necessary. These are the opening words of the Declaration of Independence by Thomas Jefferson. And a string like this of characters in natural language, such as English, doesn't have to get very long. And as the string lengthens, the probability of its origin tracks with that, right? And as the string gets longer, the probability that that string could have arisen another time independently goes down dramatically, in fact. So I'm going to say to those students, I call them in and I say, look, if you're going to cite Jefferson, or if you're going to quote Jefferson, you've got to cite him. This is not your work, right? There are not 3 Mona Lisas. There's one in the Louvre. The other 2, if we see them in London and Madrid, we know are copies, unless, the original is on tour, which, the Louvre would never allow. It's very hard to see it, there in the gallery in Paris. We see the Mona Lisa in London. We see the Mona Lisa in Madrid. We know that it's a copy of the original. All right. So I want to, again, credit the strength of these probabilistic intuitions about matching patterns. So if we go back to our 2 scenarios here, this is just hopelessly improbable. We're not even going to give it a serious thought, right? Well, I'll clue you. You need to focus on this, the origination probability, because that is what's driving your intuitions. We'll come back to that in a moment. All right. What probabilities do we need to make this kind of comparative inference work? In other words, to eliminate independent origins as a plausible scenario. All right, let me do a little mini thought experiment here with you. The mineral quartz, here's a beautiful quartz crystal, has a chemical formula, SiO2, silicon dioxide, and it forms crystals with a hexagonal prism geometry. My younger daughter teaches geology, high school science, earth science and geology in New York. And she has quartz crystals that are gorgeous, right? They form this wonderful hexagonal prism geometry. Now, quartz, this object, this natural kind, occurs everywhere on Earth, wherever and whenever the antecedent conditions are right. So you have ions of silicon and oxygen in solution in the right ratio under pressure and heat. You can grow quartz. In fact, watch manufacturers do this. Big vats. There's a recipe. I can give you the recipe and you can grow quartz for yourself. You can, in fact, do it in your own home. They won't be very big and they won't be very pretty. But if you have a kitchen pressure cooker, I can give you the recipe for quartz and you can grow these. All right. Keep that fact in mind. All right. There's a deterministic pathway to this particular natural kind. Now, let's put quartz in our comparative scenario framework here. Do we infer an quartz? Of course not. Why? Right? We inferred a single Mona Lisa. We never infer an quartz. That is, the Greek prefix meaning original or primal. We don't, because quartz happens, right? If I find a quartz crystal in South Africa and a quartz crystal in Sweden, I'm not going to infer a common ancestor for them, because the probabilities here are sufficiently high that this will occur deterministically with a probability indistinguishable from 1 when the antecedent conditions, the right antecedent conditions, are present. Okay. Now, if you don't remember anything else about this presentation, remember this slide. It is the origination probability, not the matching of features, between object A and object B that leads us to infer a common cause. So, why do we infer a single Mona Lisa, right, in the Louvre in Paris? Because Leonardo had to sit at an easel with his pigments and his paints, right? And I forget the name of the woman he painted, but there she is sitting in the room, right? And there is a high origination improbability associated with the origin of that deposition of pigment on board, giving that enigmatic smile of that we call, sort of common terms, the Mona Lisa, right? You need Leonardo, you need his studio, you need her, the subject. There's a lot of conditions that have to be satisfied to get the Mona Lisa. So imagine the object X here is balancing on the tip of this point, just balancing there, ready to be tipped off, right? So that's the reason for this schematic, is to give you the sense of the extreme improbability associated with the origin of that particular artifact, all right? So that the matching that we see ends up actually not being the main epistemological determinant of our intuition. It's this. It's the high improbability that it could happen even once. All right. A helpful way to think about this is in terms of a lottery wheel. So this basket here is filled with wooden balls with numbers on them. And when we turn the crank, we are randomizing in a way that we cannot follow, right? So there's no deterministic or algorithmic way for us to track those balls bouncing around. So we've introduced a randomizing process, and we crank, and then we sample, and we get a particular sequence of numbers that we will never see again. All right. So this is a helpful way of thinking about these high origination improbabilities in terms of long Markov chains of events that will not repeat. Okay. Now, why do we make this inference? Well, what happens is we take that improbability and we bring it over here, and now the product rule applies. Okay? Meaning that this scenario is going to lose every time as long as this pathway is improbable. And the reason for that is the product rule in probability theory for independent events looks like this. Here's our lottery basket. Here it is again. If these are independent events, so we turn the crank here and we sample the balls and we get a particular numerical string. And then we put all the balls back and we do it again, and there's no funny business. So these are genuinely independent events. We are going to have as the product, because these events are independent, an overall probability for the scenario, this overall scenario, that is the product of this small probability and this small probability. Now, this rule in probability theory formalizes our intuition that we use in daily life, really, right? We catch plagiarists with this. And I mean, you can do this for yourself. Think about cases where you say that could not have happened independently. That had to have some kind of template that I can find that will show me the original improbable pathway. This rule in probability theory formalizes that intuition that the Mona Lisa could not have been painted twice and so forth. So the product rule applies here. This pathway is very improbable, and we put it over here. The product rule holds, and this is going to lose every time. Again, this is now the third time I've said this. I want to give all the strength due to these intuitions because they are reliable for us. And you can see these actually in the evolutionary literature. So in a really surprising way, throughout much of the 20th century, neo-Darwinians such as Ernst Mayr, Richard Dawkins, Jacques Monod, and many others, Francis Crick, saw the origin of life as a very lucky event indeed. Minuscule odds, to borrow Christian Schwabe's term here, such that a second origin of life, identical in its molecular details to the first, would be subject to the product rule in probability theory, and you're just going the wrong direction, right? If what you want is the most plausible or parsimonious explanation for the origin of life and its diversity, invoking a second origin of life, if the original odds were something like this, would just be crazy. As Schwabe puts it, no serious thought must be wasted on such a proposal. Now, this may be counterintuitive, but pay attention. Watch what happens now when the origination probabilities go the other direction. So you can think of the probability as a little red wooden bead on a wire. It's in the probability interval. The wire is stretched in the probability interval between 0 and 1. For most neo-Darwinians, that bead was sitting over basically next to 0. Jacques Monod put in Chance and Necessity, he said, the antecedent probability of the natural origin of life is effectively 0. We're just lucky to be here. In fact, some copies of the paperback book for Chance and Necessity in English show a roulette wheel. All right, take that bead and slide it away from 0 and slide it over towards 1. As these origination probabilities reach unity, here's another helpful metaphor, a funnel, right? So I put something into the funnel, sand, whatever, and it's going to be channeled down, coming out in one particular position. So you can think of this as a deterministic funnel, maybe in physics, in chemistry, that's going to channel the origin of life down to all these chemical events involved in the origin of life down towards a single solution. So we've got now a deterministic pathway to object X, let's say Luca, right? Well, we can import that deterministic pathway over here to our independent origin scenario. 1 times 1 is 1. So if we apply the product rule over here, as we should if these are independent pathways, and remember, this is what we observe up here. Observation is similarity between A and B, A and B. We're inferring back to what happened if we have a high probability or deterministic scenario for the origin of life. There's nothing that will let us distinguish independent origins and common ancestry. So you can use the quartz mini thought experiment as your model for this, right? Quartz happens. What if we inhabit a planet, again, thinking naturalistically now, where life happens, given the right antecedent conditions? Okay, as probabilities reach unity, these scenarios, independent origins versus common ancestry, become indistinguishable. Again, that's why we don't infer in Ur quartz. Given the right conditions, quartz happens, it occurs independently. Now, what are the consequences of this way of thinking about improbable pathways? What are the consequences for evolutionary theory? Okay, let's go back to the intuition that's most widely shared among evolutionary biologists. Here, common ancestry is strongly favored because any pathway to life is going to be highly improbable. So the product rule applies here. This is going to lose every time. All right. If we change our intuition, if we slide our bead away from 0 and over towards 1, nothing favors common ancestry probabilistically under this scenario. And we're going to need some other line of evidence other than matching up here, right? Because matching is not really determining our inference. What's determining our inference is what number, what value we assign to this pathway, to these pathways. Now, what does this mean? What this means is reconstructing Darwin's tree of life, beginning with observations and inferring your way back to the most plausible history for what you see, requires either a very improbable origin of life, effectively, as Jacques Monod said, indistinguishable from zero. We're just lucky to be here. Or some bottleneck or singularity after the origin of life, such as the fixation of the genetic code. So this geometry, the geometry that you'll find in a biology textbook, which is just represented here in PowerPoint by a cartoon, but it's the monophyletic tree of life that is textbook orthodoxy. This geometry rests on an improbable origin of life. Or if you say, well, maybe abiogenesis happened with a much higher probability. If you're going to invoke a singularity like Luca, you're going to need some bottleneck to do that. So you could say, well, there was a small probability bottleneck at Luca, even if below that, in the prebiotic milieu, life was forming all the time. To get this monophyletic single tree geometry, I'm going to have to invoke some kind of bottleneck, and I'll do that at Luca. And typically in the literature, this is done with respect to the fixation of the genetic code. So Richard Dawkins, who I must commend for his clarity, when I taught writing at the University of Chicago, I would use a chapter from The Blind Watchmaker on the origin of bat sonar. I think it's the second chapter. So beautifully, it might be in the first. Anyway, it doesn't matter. It was so beautifully written. Just a wonderful example of expository prose that I gave it to my students and said, if you want to write well, write like Dawkins. So he's very clear here in The Blind Watchmaker. He says, how do I know that all life on Earth shares a common ancestor? Because there's a universal genetic code. Now, I don't have time to talk about this today. That is false, right? All organisms do not possess the same genetic code. Don't tell people they do. And please, as I said in one of the earlier segments, do not use the nonsense phrase nearly universal. I won't belabor that, but it's not the case that all organisms share the same genetic code. But at the time that Dawkins was writing, the discovery of the non-universality of the code was really still on the horizon. A few examples had been seen, but they were sufficiently few in number that one could say, well, it's in the mitochondria and they don't really count. But today, in October 2021, there are so many variant codes that you have to go look them up if you're working with a group that has a variant code. In any case, let's give him the credit for the argument and say, let's assume that there was a universal code. He's in the neighborhood of what he needs to argue here. For Dawkins to be right, the origin of the code, even once, must have been exceedingly improbable. Because remember, as you move your bead on the wire away from zero and towards one, funny things happen to your ability to infer reliably that a common ancestor existed. So many years ago, in conversations with Lee Van Valen, one of the members of my dissertation committee, I said, Lee, what if we went 500 years into the future in a time machine, and we found ourselves in a high school biology class, advanced biology class, and the lab exercise for that day was to synthesize the genetic code, right? And the students have their, 2,500 Common Era equivalent of a lab notebook and all their apparatus, right? And the teacher is telling them, by the end of the day, you should all have the so-called canonical code in your flask. If you don't, you didn't follow the recipe in your lab manual. Now that seems science fiction, right? But think about the synthesis of urea prior to the early 19th century. It was thought that urea had to be produced by a living thing. And Wohler, I believe in 1828, it might have been a little bit later than that, discovered a non-organic pathway to urea, changing the probability of the non-organic probability of that origin of urea or the formation of urea from 0 to 1 overnight. So if you imaginatively put yourself in a scenario where these pathways move from 0 to 1, what you're saying really is we don't, and again, thinking as naturalistic evolutionists now, we don't know the pathway now, but we might well know the pathway 100, 200 years from now, and that will affect how we infer the history of life. So, getting close to wrapping up, I think I'll be able to make it on time. I'm almost done. To root the tree of life, the origin of life needs to look like what Iris Fry, is an Israeli philosopher of science, calls a near miracle. And I'll say more about that on the 18th. Well, what implications does this have for the naturalistic project of explaining life on Earth and its diversity? All right, I apologize for the humor here, but the joke is illustrative. So here's an old joke. You may find funny. If you don't, I apologize. So a rabbi, a priest, and a Presbyterian minister, and this is in the United States, not in the UK or Pakistan or anywhere else, right? It's a very American joke. A rabbi, a Roman Catholic priest, and a Presbyterian Protestant minister are out in a boat. They're friends fishing one day a mile from shore, and they run out of beer. Okay? So the priest, the Roman Catholic priest, says, "Don't worry, I've got it." Climbs out of the boat, walks across the water to the shore, to the car, to the cooler, gets the beer, walks back to the boat, and the rabbi is fishing away as is, this is the most normal thing on earth. The Presbyterian minister is flabbergasted, but he doesn't want to let on that he is flabbergasted. So he's just like, I can't believe I just saw a miracle, right? All right. Then they run out of food. Now the rabbi says, you know what? Don't worry, I've got it. He gets out of the boat, walks across the water to the cooler, gets the sandwiches, comes back. The Presbyterian minister is beside himself now with shock, right? He can't believe this has happened. 2 miracles. First the priest, now the rabbi. Okay, then they run out of bait. Right? No more night crawlers, no more worms for fishing. And the Presbyterian is not going to let the Protestant world down. Okay, he's going to show that he too can do this. So he says, I'll get the bait. I'll go get the worms. Climbs out of the boat, steps on the water, disappears under the waves, never to be seen again. And the rabbi and the priest keep fishing, and they say, it's a shame Pastor Bob didn't know where the rocks were. All right, I said it wasn't funny, but it's illustrative. Okay, they go on fishing. What's going on? What's going on is there's a hidden deterministic pathway that takes a 0 probability event and makes it a 1, as long as you know where the rocks are. It's not a miracle, right? The priest and the rabbi knew where the rocks were. Well, what's the relevance of this to the naturalistic project of explaining the origin of life in relation to its diversity? Think about yourself as an origin of life researcher. You're working on, let's say, the formation of RNA, or formation of cell membranes, or some chemical aspect beginning in a prebiotic milieu, going towards a cell. You want those pathways to be as probable as they can be. You want that bead as far away from 0 as you can make it. You're going to shove it as far as you can get it towards 1. You're going to be looking for the rocks beneath the waves, the deterministic pathways, because that's your only hope of doing science, right? You can't do science on a near miracle. When probabilities get sufficiently small, especially in laboratory or bench work, You can give up doing laboratory or bench work because the whole point of doing experiments is that you are capturing conditions that exist independently of you and independently of luck, right? Synthesis of urea is a good example. A student in an organic chemistry lab today can perform an experiment with a probability indistinguishable from one of synthesizing urea, where prior to Wohler in the early 19th century, that was a probability zero event. So again, within the framework of naturalism, you want to shove those beads over towards one. Get them as close as possible. Raise these numbers. Now, what's the problem? The problem for evolutionary biology is they are working their way back down from observation via a series of singularities that have small probabilities attached to them. So next time, I'll talk about this not only in relation to the origin of the ribosome, but at events like the origin of the eukaryotic cell, right, where you have an alpha proteobacterium engulfed by some unknown ancestor to eukaryotes, just got lucky, and that was the beginning of the story of the origin of mitochondria. So you're working your way back down from observation towards LUCA, chaining together small probability events where you get lucky over and over. Meanwhile, tunneling up from the bottom are your chemistry colleagues who are trying to raise the probability as high as possible. These two paths of research are therefore fundamentally at odds with each other. And when one realizes this, as I did during my doctoral work, I realized that the naturalistic program of explanation, the full program, not just evolution as a biological theory, but evolution in the most general sense of once upon a time there were no living things. Then about 3.8 billion years ago, some of them got up and running, and they've provided, or one of them was the lucky predecessor of all life that we see today. That within that larger framework, that naturalistic framework, there were deep conflicts in probability intuitions and how this story was going to be put together. So next time, we'll look at the ribosome, which, if you're like me, you're going to fall in love with these details. I'll be referencing in particular the work of the Lauren Williams lab in Georgia, but other groups as well, and some really world-class puzzles that have received far too little attention. But we'll do what we can to draw more attention to them. We'll look at some other events like the endosymbiotic theory for the origin of cell organelles. But keep in mind that actually this mode of reasoning to singularities is really pervasive throughout the whole evolutionary tree. So the origin of body plans has this character, and so forth. Anyway, I've run perhaps a little bit long, but that is it. That's the last slide for today.
Brilliant. That was really lucidly explained. I think the best way to summarize the impact, the implication of what you've explained is to take the rug from underneath this supposedly very powerful argument that you've got two different sequences of DNA. It's almost self-evident that, you know, who would dare you know, challenge this. So I really love the way you've explained that. I just wanted to highlight a few things so that everybody really gets it, because there was a lot of detail that you covered. So let's recap to what the Darwinists, the ones who subscribe to the universal common ancestry idea, would be proposing. They would, in terms of, say, human chimp ancestry or any other sort of claim about common ancestry, they would point at usually anatomical similarities before, and then they would obviously later on point at genetic similarities. we could actually say, well, what is the null hypothesis here, right? So what if this was to be challenged? What is it likely to be? And I heard you say in another talk some years back that they would say something like the null hypothesis is randomness, right? And well, that's just as unlikely as saying, okay, well, if you're to go down the road and pick up a lottery ticket, that is, say, scenario A, and say scenario B is you're to walk down the road and you're to be hit by lightning, and then you carry on walking and hit by lightning again. Well, the second scenario is so much more improbable than winning the lottery. So winning the lottery is quite probable. So when you have these very ridiculous what's it called, comparisons, right, that we would expect randomness, then it obviously becomes predetermined that you will win the lottery. Likewise, it's a given. We find this in the God delusion. Dawkins speaks about this, and we find many of the other Darwinists state it, and they assert it without argumentation that it is just so improbable. The origin of life is so improbable. And as a point of admission, when I was looking into this area a few years ago, I accepted that as face value. I didn't challenge it because it just seems so self-evident and so true.
Well, this is one of the reasons that I carefully separate out, as we did it in the first part of the talk, the hypothesis of design from the naturalistic framework. Because if you look in the work of Lev Berg, he has a book that was reissued by MIT Press, published in Russia in the early part of the 20th century, called Nomogenesis. He did not accept universal common descent. And the main reason he didn't was in relation to this question of these origination probabilities. And he said, if I imagine a world in which the origin of life is not a lucky one-off, right? You just happen to hit the cosmic lottery. We're just lucky to be here. I'm putting this in sort of 2021 terms, but it's beautifully written. And he actually was a mentor to Theodosius Dobzhansky, of all people. Dobzhansky wrote the introduction to the MIT Press translation and reissue of Nomogenesis, of Berg's book. In any case, what I realized is there was this unoccupied part of the theoretical landscape where, instead, thinking again strictly now within the framework of philosophical naturalism, where instead of invoking luck, which is what really this devolves to, right? A high origination improbability means you've got a long chain of events, none of which really wants to happen, but somehow they do. To me, luck is the end of science. And it's one of the reasons I dislike the multiverse hypothesis, because it has these just, undisciplined appeals to luck. And Christian de Duve actually makes the same argument as Berg and people like Stuart Kaufman, in fact. De Duve says, the Belgian Nobel laureate in medicine or physiology, he said, imagine that there are 1,000 independent steps to the origin of the first cell, from basic chemistry to a functioning cell that's able to reproduce itself. 1,000 steps is probably much too small a number, but let's assign each of them odds of 1/2, coin flip, right? Each of those independent events has a coin flip probability associated with it. Coin flip is a pretty good probability, right? You've got 50% chance of being right. He said, long before you get through those 1,000 steps, if the product rule applies, the joint probability is going to be something you will never see in this universe. It's just never going to happen because that product becomes so small. So de Duve's argument was, it had better be the case, if you want to do any science on the origin of life, that the probabilities of those independent events are effectively one. You've got to assume, right? If you
Yeah.
really, if you hope to have any insight into how this actually happened. And
Yeah.
again, once I realized this and read Stuart Kaufman, who has the same view, which is we should not, as evolutionists, think about the origin of life as a lucky one-off event, then you realize there's this whole landscape or whole region on the theoretical landscape that's been largely neglected because the strength of the Dawkinsian, we're just lucky to be here. The strength of that intuition is so great that it overwhelms people when they really shouldn't
Yeah.
accept it. I'm sorry for going on and on about that.
No,
But
no, absolutely. I mean, you mentioned Kaufman. I'm assuming you're referring to the one behind the evolution by self-organization idea.
exactly. And
Yeah.
if you read his work, in particular the 93 book from Oxford, The Origins, I think it's The Origins of Order. I'm sorry, I don't remember the title at the moment. But other of his essays and books, he has a view which is almost Aristotelian in the sense of a kind of natural teleology for the origin of life.
Yeah.
And of course, this spills over in all kinds of interesting ways into, astrobiology or a science without a subject, actually, which is life elsewhere, right? Again, were I a philosophical naturalist, I would assume as a heuristic necessity that the pathways to life are not where the bead is by zero, but somewhere over much closer to one, simply to undertake science.
Yep. Absolutely. So in terms of the real life, everyday interactions between intelligent design proponents and universal common ancestry proponents, this is something we could give as a general reply to those claims of homology being self-evident because we've got this sequence of DNA or this biochemical structure is similar to this. Also, something interesting about this particular approach is that their entire argument is essentially grant us one miracle and we'll explain the rest, right? That's essentially what they're saying, and that's not something I just it's a phrase I heard somebody claim against them. So if we allow this type of improbability within science, then like you mentioned, the whole foundation of science itself, not just evolutionary biology, is up for question, because if we want to be consistent and not have this selective application of improbability on this event, then we could just do that with a whole bunch of things in physics, chemistry, biology. We could simply say, well, okay, this particular thing is incomprehensible. We won't be able to rationally access how this took place because it's so improbable. And we could just then have these blocks to science, right? So it has wider epistemic implications, not just for what we're discussing right now.
Oh, I couldn't agree more. In fact, biology class would be very short. Right? It would effectively be the length of time it takes to write the word luck on the blackboard, and then everyone could go home. To me, and I'll put my cards on the table here to use that hackneyed metaphor. Appeals to naturalistic near miracles are the secular equivalent of mysticism.
Yep.
Right? Because they are opaque. There's nothing to transmit in the way of reproducible knowledge. When I go aboard an airplane, and the pilot comes on the intercom and he says, "The mechanics on the ground tell me there are 10 defects on this plane which may endanger our flight, but I'm counting on luck that they're not all going to failed. No one's going to stay in their seat, right? It's abandoning practical reason to do that. And I think the problem we have in 2021 is the implications of design, or let me put it this way, the evidence of design, not only in biology, but in cosmology and other fields, are so strong. But the next step, namely that there is a transcendent intelligence who is responsible for our existence, is that next step is so distasteful to modern sensibilities that very smart people are willing to embrace Mother Chance, Dame Fortune, right? And once she grasps you in her arms, she'll drag you down. And it
Yeah.
is. I'm so glad you said that, Subor, because it is destructive of things that all of us should want, which is a rational, well-grounded science where evidence, not appeals to luck, runs the show.
Absolutely, absolutely. And I'm thinking what Carl Linnaeus would actually say of these sort of contemporary arguments from homology when it comes to, say, genetics. So Carl Linnaeus, as you mentioned, was a creationist, an intelligent design proponent. We still use his system. So he saw the similarities between human beings and chimpanzees and other forms of life. But he didn't obviously believe in universal common ancestry. Now, what's interesting is today it's used as a point of surprise. Isn't it incredible that there is similarity between the DNA sequence of a chimpanzee and a human being? Well, Linnaeus would say, well, I classified them anatomically to be similar, so why on earth would I assume their genetic code wouldn't be similar? Why is that a surprise? And I heard you in another talk say that Darwin's theory is a theory of transformation, not a theory of similarity. And I guess what we can add by this talk is that if it is a theory of transformation and it's not just a theory of, hey, look, things are similar, then that transformation has to include what Darwin completely forgot to apply, which is the origination probabilities, which in a way sucks the life out of the origin of species.
Yes. I'll tell you an interesting experience I had when I was an undergraduate. I was in the honors college at the University of Pittsburgh, and Niles Eldridge, one of the authors of Punctuated Equilibria, came from New York to do some seminars in the honors college, and we went to dinner, and he was sitting right across the table from me, very cordial. And these questions about homology and the structure of the tree of life came up. And he said something that struck me. He said, really, Paul, it all devolves, no pun intended, it all goes back to the origin of life. And if you think about that, it's true, because at the origin of life, the features that make evolution possible must all be present jointly in the same entity.
Yep.
And those features are not simple. So just a couple of days ago in the bioRxiv, this beautiful paper was, a pre-publication manuscript was posted by a group at Caltech, solving at nearly atomic resolution the cytoplasmic face of the nuclear pore complex. Okay, I remember learning about the nuclear pore complex, that is the portal between the nucleus and the cytoplasm in eukaryotes, out of which, for instance, messenger RNA strands pass. I remember learning about this, as a student, and actually being involved in a movie, Unlocking the Mystery of Life, where we animated it. That structure is so much more complex than anyone imagined. It staggers the imagination. And that's the case for even a single bacterial cell. So Eldridge's point was, there's something about the origin of life as an event that is special. And for me, the most compelling reason, scientific reason, laying aside theology, laying aside philosophy, easily the most compelling reason to be a design theorist and to take that part of the landscape that I described earlier and focus there is the origin of life is the shoal on which the naturalistic program of explanation just wrecks.
Yep.
And it's not fun to be in the philosophical and scientific minority with respect to intelligent design. It's hard to get papers published. It's hard to get the academic or financial support that the mainstream enjoys. But I would never want to solve the problems that they face, such as getting a cell from chemistry. You can have that one. All right. It's just not going to happen.
Absolutely. And I guess, Paul, you don't want to be associated or you don't want to be seen to be associating with people who would, if you were to defend the naturalistic sort of fairy tale, ideas like panspermia to explain, the complex origin of life, and panspermia for anybody who's actually, Paul, I think you can explain it better than I can. But these are the sort of absurd sort of ideas which are being proposed because they can't explain the complexity of life.
Well, Francis Crick, who seriously proposed panspermia both in primary literature publications, but also in a beautiful, elegant little book in 1981 called Life Itself.
Oh, yeah.
Crick is a scientific hero of mine. I regret never having a chance to meet him and thank him for what he did. But Crick, because he was working on the naturalistic side of that divide, right? In Life Itself, Crick says there are so many problems chemically with getting the structures that we need to build a cell on the early Earth that it is plausible. In his estimation, it was plausible and reasonable to say it could have happened on another planet with different conditions, and it could have been sent here by an intelligent species elsewhere in the galaxy deliberately. How does one end up in a position like that? Well, again, if you go back to that original fork in that logic tree, once you say design is off the table, then the resources that you're left for explanation are inherently limited. So panspermia, I think, excuse me.
No worries.
Panspermia is, given a naturalistic framework, I would say, yeah, it's reasonable. Why not? Right? But I don't have a naturalistic framework. And the secret, I probably shouldn't say this, but the secret that intelligent design people have is that we can have so much more fun than our naturalistic colleagues because we get to use everything of value that they discover. There it is. It's in nature, right?
Yep.
Those processes, those mechanisms, that knowledge is there in nature. Plus, we get this great universe of teleological and design-based analytical tools that they, by their own choice, have forsworn.
Yeah,
I'm greedy, right? I want the bigger set of toys and tools.
Absolutely. I mean, we're not epistemically caged like that. And for anybody who would think that panspermia is maybe dated or Darwinists wouldn't actually use it, I would recommend you watch No Intelligence Allowed. I'll put that in the description. Paul is there, Jonathan Wells, other intelligent design proponents, and in the end, Richard Dawkins actually refers to panspermia as a possible explanation for the origin of life. So this isn't just a dated idea. It is something that they have to run back to if they are pushed in a corner. And so, Paul, I really don't want to take more of your time because we have more sessions planned. So for everybody watching, this is a series that we are doing on Universal Common Ancestry. I'm very grateful to Dr. Paul Nelson for giving me his precious time. And we will be back on 18th of November to go over part 4. So thank you, Paul. It's been a pleasure.
Anytime. I'll see you guys on the 18th.
All right. Assalamu alaikum wa rahmatullah.